P7 is called complex numbers. Now I mentioned the word complex last time about complex fractions. Complex does not necessarily mean complicated in the ideology of what we're doing. But these are called complex numbers. A complex number is numbers that have the form a plus bi, where a and b are real numbers, and I is the imaginary number, where I is equal to the square root of -1, or I squared equals 1. The first couple we're just identifying. Do I have a real number or do I have an imaginary number? Imaginary corresponds to complex. And they want us to write it in the form a plus bi to represent it at the end. -72. Real or imaginary? Real. We've used -72 forever. No problems on that one. This is a real number. You can still write it in the form that they're talking about. It's just that it's -72 plus 0i. It's not very exciting, right? There's just 0 times I, so that's how we write it. How about the second one, number 2? It's imaginary, or you could write complex. The directions here say to use the word imaginary, so we will. And again, how do I write it in the form a plus bi? Well, we write 0 because I don't have any any constant that's written without the I attached. And then we actually write it, this looks kind of funny, but we write it with the square root of 5 in front and the I afterwards. I'm not a big fan of writing it in this order, the one we just wrote down, because I think there's a real tendency to get sloppy and accidentally make it look like the I's underneath the radical, and it shouldn't be. The order that they gave it to us in originally, there's no chance of that happening because the I is written in front of the radical. But they're both correct. There's nothing wrong with them as long as we're being careful as we're writing them down. Okay, so we have real, we have imaginary. There's a couple other things that we can do. Simplifying with complex numbers is relatively simple. It looks a lot like simplifying with polynomials. The like terms are the ones that have the like pieces next to them, right? So if they both have i's next to them, they're alike. If they both don't have i's next to them, then they're alike. So as we take a look at addition and subtraction, it works exactly like it would with polynomials. We say, hey, look, I have addition. If I have addition, I just combine like terms. These two terms are alike, namely the +5 and the -3. And if I add them together, I get 2. And these two pieces are alike because they both have an I attached, much like if they had an X attached. So I have +2i and -6i, and those combine together to give me -4i. Just like we would if we had X's. It's nothing any different. Same thing happens with the subtraction. We need to distribute the subtraction through. So I have 6 minus 7i. I have -3 and +4i. And then I combine like terms again. So I have the 6 and the -3 that will combine to give me 3. I have a -7i and a +4i, which combine to give me -3i. Okay. It's almost just like we took away an X, we put in an I, nothing changed except the name. That's what it looks like with addition and subtraction. And multiplication has one small difference. So it's going to start out the same. We're going to distribute, we're going to FOIL, whatever language you would like to use. I'm going to take my 3 and I'm going to multiply it through. 3 times 5 is 15. 3 times -2i is -6i. So far, so good. We're going to do the same thing with the -i. So, -i times 5 is -5i. And then -i times -2i would be a +2i squared. Okay, nothing any different so far. Just like we did with x's. Also, just like we did before, the negative 6i, the negative 5i, those can combine. It's negative 11i, right? So here's the difference. The difference is with the I squared. Back in the original piece that I showed you, I told you that I squared is actually equal to negative 1. So anytime I squared shows up, and now it has, I actually will replace it with the value negative 1. So what I actually have here is I have 15. I have that negative 11i I mentioned already. And then instead of having positive 2i squared, I really have negative 2. Because I squared is equal to negative 1. My last step will be to combine the 15 at the beginning, the negative 2 at the end for a 13, and negative 11i. So the difference is we don't end up with exponents when we multiply these out. Now it goes a little further than that. I showed you how we don't end up with squareds. We won't end up with cubes or any other powers of i's either. And we'll get there shortly. So this one down here at the bottom actually feels, again, kind of like what we did with our variables when we had the variable x. We talked a little bit about, but it feels more like what we did with radicals, and we had radicals and denominators. So do you remember when we were working with things where we were dividing radical expressions? And we talked about the fact that we don't want radicals left in the denominator. Okay, do you remember that? No radicals left in the denominator. So we did this thing where we multiplied by what was called a conjugate. Okay, it was the same thing, it just had a different sign between it. So all the same pieces were in the denominator, just an opposite sign. We're doing that same thing here as well. So if I have 1 plus 4i, the conjugate is 1 minus 4i. And if I do it to the bottom, I have to do it to the top. Okay, so it's just like radical expressions. I multiply by conjugates. So, as I'm looking at the bottom, the reason that I'm going to do that is because I won't end up with any i's left. So check this out. I have 1 times 1 is 1. I'm going to write it underneath here so that don't run out of spaces quickly. I have 1 times negative 4i, which is negative 4i. I have this 4i times 1, so that's positive 4i. So those are going to add to 0, right? At the end, I have a positive and a negative, so that's a negative. 4 times 4 is 16, I squared. But what's I squared? It's negative 1. So at the end, I really have a negative 1 times a negative 16, so there's a positive 16 right here. So I have a 1, I have a 0, and a positive 16. All that adds together to give me the simple number 17 in the denominator. No i's. The top is not going to collapse as nicely. I'm still going to have i's left, but no I squareds, right? I mean, I can simplify that piece of it, but I will still have some i's left. So let's distribute the top out now. 2 times 1 is 2. 2 times negative 4i is negative 8i. Now we're going to do the negative 3i. Negative 3i times 1 is negative 3i. I have a negative 3i and negative 4i. Well, negative times a negative is a positive. 3 times 4 is 12. And I have I squared. Yeah. So right here, I really don't have negative or positive 12i squared. I really have, after I change this, negative 12. So let's combine the pieces. I have a positive 2 and a negative 12, which gives me negative 10. I have a negative 8i and a negative 3i, which gives me negative 11i. And it's all over 17. If you flip to the back of the book, it might actually do this. And write it like this. I absolutely do not care whether you do that or not. Okay, so if you look at the back and it does this to it and you really want it to match the back of the book, go for it. If it doesn't bother you, you can leave it in the fractional form combined already anyway. Okay, any questions on that one? Yes, Allie.
To get the 2 minus 8i minus 3, etc., do you have to cross multiply the 1 plus 4i and 1 minus 4i?
Are you talking about down here, Allie?
Yes, to get the next problem next to it.
Yeah, so we aren't cross multiplying. What we're doing is we're multiplying across it, right? So if I multiply the 1 plus 4i and the 1 minus 4i, I just wrote it out below here so that I could consolidate. And if I multiplied out the 2 minus 3i and the 1 minus 4i, I end up with this one. So I'm distributing or I'm foiling to get those individual pieces. Am I interpreting your question correctly?
Yes.
Okay. All right, I mentioned a moment ago that when you have i's, you'll never have powers of i's left in your problem, right? And I showed you what happens when we have I squared. The reality is that it works for all powers of i's, but in a little bit different way depending on where you are. So let me show you what I mean. I can't write I any differently if it's just by itself. It's just I. But like we've already encountered, I squared is -1. So this is what we have so far. Now the kicker is that when I have I cubed is the same thing as I times I squared, right? But what is I squared? -1. So this is really, this piece is -1. So this is actually -I. Because I have an I times -1. I to the 4th could be written as I squared times I squared. What's I squared? -1. So this is really -1 times -1, which equals 1. And we can always break them down like this. I to the 5th, excuse me, is I and I to the 4th. But what is I to the 4th? 1. So I to the 5th is really just I. I to the 6th, well, that's I squared and I to the 4th. I squared is -1. I to the 4th is +1. So I'm back at -1.
So it's just 4?
Yes, I'm so glad you noticed that, Caleb. You're exactly right. There is a pattern, which is why I wanted to show you 6 of them. There are only 4 things that can happen. I can get I, -1, -I, or 1, and then the pattern repeats. I, -I. Even without doing it, if I asked you to do I to the 7th, you should be able to tell me it's -I, and I to the 8th is 1. The pattern continues. Now, it's valuable to notice that anytime I have an I to the 4th showing up, it's sort of like the best one, because multiplication by 1 is really easy, right? So let me show you what happens with the 19. Here's your best way to break it down. As you're looking at them, I'll do one of these and then I'll pause. If I can take 19 and I can break it down into something that's a multiple of 4, that's really helpful. Well, 16 is a multiple of 4. Right, think about your multiplication tables. 16 is one of those. So if I to the 16th and I have I cubed. Why do I have 16 and cubed? Well, because they have to add to 19. Right, that's an exponent property. Anything that's a power of 4, like a multiple of 4 as a power, is going to be equal to 1. So this piece is 1. And you know what I cubed is, because we've written it down over here. I cubed is -I. So all of this multiplies to -I. We'll pop back in with number 8 next time and do the same thing, and you can continue from there. So I'll make the adjustment inside of Canvas, so P6 is the only one due. Starting P7 would be a good idea, but if you get to the powers of I, you can probably push pause, and we'll continue our discussion of that next time.